So it's a pleasure to introduce Mostovoy from CINVESTAV in Mexico City, and he's going to talk about encoding nodes with diagrams.
Thank you. It's a pleasure being here. So what I'm going to talk about is a joint work with Misha Polak. And well, to tell the truth, it's mostly the work of Misha Polak. But since my name appears on the paper, I feel that it's my job to advertise this construction. So, knot theory is a very strange part of mathematics. Knots seem to be, well, it belongs to many parts of mathematics at the same time without really being part of any of them. So a knot is a geometric object. It's an embedding of a circle into R3, for instance. That's one definition. So it's a geometric object. The knots are studied up to isotopy. Well, let's say smooth homotopy, that could be. So it's a topological object. And knots can be conveniently drawn on the blackboard. So this is a projection of some knot, of a trefoil knot on a two-dimensional plane. And this is the way people encode knots normally. They just draw the knot projections indicating the overcrossings and undercrossings. So knot projections, they can be considered modular sum moves. And these moves, well, there are, of course, just continuous deformation, smooth deformations of these projections. This is one thing that we can do without to such a diagram without changing the isotopy class of the knot. And there are certain combinatorial moves that are called the Rademeister moves. There are three of them. One of them is something like this. A loop can be untwisted. The second one is like this. These two branches can be pulled apart if they are not linked. And the third one is the interesting one. It's more interesting, let's say, than the other two. And that means that if you have three branches of the diagram that cross at 3 points which are close to each other, the branch that is behind can be moved through this crossing point. So this is the same thing as this. So this may make us think that this is really a good combinatorial way to encode knots, but plane diagrams are not really combinatorial objects. They're geometric objects. They're curves in R2. And it turns out that it's not really 100% trivial problem to encode these diagrams. So the way people encode these diagrams, well, encoding, I mean, by encoding, I mean some really combinatorial object. I mean, not something that, I mean, this thing, a curve in R2 without triple self-intersection, it's not really an encoding, it's a description. So probably the nicest way to encode these diagrams. And
so an encoding you can put on a computer.
For instance, I mean, again, I'm going to draw a diagram instead of, but this diagram can be encoded on a computer, that's right.
Encoding the way you can change into the key equivalent weight, for example?
Right. I mean, well, I want to, yeah. What we really want is some kind of good combinatorial encoding of a plane diagram of something like this, which would have some kind of randomized moves, which will also be combinatorial in the nature. But I mean, it will be clear what I want because I get what I want. So, but I mean, the most usual way to encode this kind of diagrams is by means of a Gauss diagram. So what is a Gauss diagram? The Gauss diagram is a circle. There are several pairs of points in this circle, and these points are connected by arrows. And these arrows carry signs. So what do these arrows and signs mean? Well, we choose some point here. I mean, this circle is thought to be the circle of the parameters for the node. So we walk along the node and we register the crossing points. So say this is the crossing point number 1. So we draw 1 here. Then we go here and then we get to the crossing point number 2. And then we get to the crossing point number 3. And then we keep going and we get to the crossing point number 1 again. So the pairs of points correspond to the values of the parameters at the crossing. The sign is the sign of a crossing. I mean, the crossing can be either positive or negative because we have 2 branches. And so basically, locally, a crossing can look like this or like this. And one of them is positive and the other one is negative. Doesn't really matter which one is which. So the sign indicates the sign of a crossing, and the arrow shows it goes from the undercrossing to the overcrossing. So it turns out that if you have...
So this is plus minus plus, this one?
No, this is plus plus. This should be plus plus plus. I think. Because they're all the same. I mean, it's rotationally symmetric. So they should be all the same. So... okay, so such a Gauss diagram, I mean, if you have a diagram that corresponds to a node, then you can reconstruct a node uniquely. Now, there's a problem. I mean, if you draw any kind of a diagram, then it's not clear if it corresponds to a node or not. And this is actually a big problem. Well, why is it a big problem? Well, why do you want to have nodes encoded by combinatorial structures? Because you want to do some combinatorial operations with these combinatorial encodings, and one of the most basic combinatorial operations is taking a sub-object. If you have a word in a group, for instance, well, it's a sequence of generators. And you can cross out some generators, and you obtain another word in the same group. And this construction, for instance, is absolutely fundamental if you're doing, say, if you're trying to apply linear methods to your group, doing some kind of nilpotency theory. So this is really something that we would like to apply to nodes, because when you do nilpotency theory for groups, what you get is something like Vassiliev invariance, the finite type invariance. And the finite type invariants were invented for nodes originally. Then people applied them to groups, and then they realized that what they get is just nilpotency theory. So people started to look for some kind of nilpotency theory for nodes. But then there are all sort of obstacles. And here, the fact that if you erase an arrow from a diagram, you can get a diagram which cannot be realized by a node, is really quite unpleasant. So what people do is that, well, the answer, again, I mean, it's partly due to Pollack himself, like 20 years ago. The answer was to say, well, let's just forget about nodes and think about diagrams. And on the knots, I mean, on the level of these Gauss diagrams, the Rademeister moves, they look very, very nicely. So for instance, the first Rademeister move is just this. So if you have an arrow with any sign, but whose endpoints are close, this is equivalent to nothing. So let me just get rid of the...
These are the virtual nodes or what?
Yeah, so this way you get to the virtual nodes. So this is the first Rademeister move. The second Rademeister move is something like this. Plus, minus, this is the same as nothing. And these are just two parts of the knot of this circle. And the third Rademeister move is also not too difficult to draw. It involves 3 segments of the knot. So you have something like this. So you can consider, yeah, so this is the third, this is one of the third Rademeister, this is a third Rademeister move, let's put it this way. So you can take these kind of diagrams, consider the modulo of these Rademeister moves, and this is what's called the virtual knots. And the good thing about the virtual knots is that the usual knots are a subset of virtual knots. I mean, it's not obvious that the usual knots will be a subset. It's a non-trivial theorem. I mean, it's based, I mean, the proof of Polyak, Usarov, and Vir used the fact that the fundamental group classifies prime knots, which is a very hard theorem. So it's a non-trivial thing that knots are a subset of virtual knots. So this is a good thing about virtual knots. And the bad thing about virtual knots is about everything else. Like, they have been studied for 20 years. There are some invariants of virtual knots and all that, but it's kind of clear, although not very often said out loud, that the virtual knot theory goes basically nowhere. It's a kind of it's a part of mathematics that lives in itself, and unlike usual knot theory, which has connections with everything, the virtual knot theory only has connections with the knot theory. So this is really the unpleasant part of the Gauss diagrams. So what I'm going to present here is a way to encode diagrams which is free from this drawback. There are no virtual knots here. So for that, let us see. The problem is that, well, there are 2 ways to think of braids. Knots are very similar to braids. And braids are very well understood, well, pretty well understood. I mean, of course, there are open questions about them and all, but the algebraic structure of braid groups is very helpful in the study. So there are 2 kinds of braid groups. Of course, there are more kinds of braid groups. But there are usual braids that form the group Bn. This is an example of a usual braid. And this is a braid on 2 strands. And there are pure braids on on n strands. And so this is not a pure braid because it gives you a non-trivial permutation. And the pure braid on 2 strands is something like this. So basically, braids on 2 strands are generated by twists, and pure braids on 2 strands are, well, these are half twists. And pure braids are generated by full twists. And it might seem to be not a great difference, but it actually is huge. I mean, these two groups are very different.
Isn't one extension of the other?
Yeah, of course. But somehow, I mean, the pure braids, they look like free groups. They're iterated semi-direct products of free groups, and they have very nice properties of free groups. They have tons of normal subgroups, and they can be studied by linear methods. I mean, they're residually nilpotent. So the lowest central series intersects in the identity. And the braid groups, they're a mixture of this with the symmetric group. And the symmetric group is a complete opposite of the free group in the sense that there are almost no normal subgroups, and well, you cannot study them using the lowest central series directly because, well, since there are no normal subgroups, there are no central series on them. So if you want to if you want to use linear methods, which means if you want to study Vassiliev invariants, these groups are very nice, while these ones are not so nice. So when we study Gauss diagrams, really, an arrow on a Gauss diagram represents a half twist. A crossing is a half twist. So what if we, instead of half twists, we consider full twists? And that's what this talk is about. I forgot when I started. 11:42. When did I start?
You have 13 minutes.
Excellent. So what is a clasp diagram? So these clasp diagrams, they were invented by Polak. I mean, we were very slow writing this down. This is my fault, I guess. While we were writing this down, somebody else wrote something similar down. So there is a paper by someone called Hugelmeier, I think, and it has the same geometric idea, but he didn't. He sort of went halfway. He didn't get the complete result. So I will. So these diagrams are due to Polak, and that's it. So we have a circle, and we have, like in a Gauss diagram, and we have some chords with signs. They have no arrowheads. These are not arrows. These are just chords. Something like this. But these chords, they have a notion of height on them. Some chords go on top of the other chords. And I say height. It's not just some kind of local height, because I really want them to be well ordered. So this is a chord diagram. The chord diagram is exactly this thing, a circle with pairs of points, with signed chords.
So the whole chord has the same height?
Yeah. With signed chords. I mean, here you can basically think just in terms of overcrossings and undercrossings, but I mean, these overcrossings and undercrossings shouldn't give you cycles. Right? You can't have any Escher pictures with signed chords and the total order on the chords, on the set of chords. And then, of course, there are some equivalences on these chords. And to understand these equivalences, let me show you how this kind of a diagram gives rise to a knot. Then everything will be kind of clear. So each of these chords can be replaced by something like this. A full twist. And these full twists, they have to I mean, it can be a positive twist or a negative twist. This gives you the sign. I mean, the idea of I mean, you have to define what a positive and negative means. So, negative is this one. The positive is the other way. And of course, the order on the chords, it can be thought of as height. So, it gives you the idea of who is above who. So something like this. So this way you get a knot. Now there are some things there are some equivalences on these diagrams. I will say something about these equivalences in a second. But what are the clear advantages of this kind of representation? Obviously, if you erase a chord, you get some diagram that represents another knot. So there is no notion of realizability. Every diagram is always represents some knot, and that means immediately that it's a good tool to study the Vasilyev invariants. I mean, we're kind of halfway there. So we have some diagrams now, and still we have to make some calculations. What we really want is to prove something about the Vasilyev invariants. But I mean, I'm not really going to say anything about them here. So the main theorem that we get is the representation theorem in the sense that it can be proved that every knot can be represented by such a diagram, and that a short list of equivalent of moves on these diagrams really produces equivalence classes of knots. So what are the moves on these diagrams? Well, the first move is invisible, and basically it means that if you have two chords, so the first move says that if you have two chords that do not intersect, and they have the neighboring, I mean, okay, so there's one more thing I have to say. So when I draw moves on the diagrams, something which will be something like this, moves will always be of this kind. So we have parts of the circle of the diagram, and then we have some chords. So when we draw the chords on the move, all these chords are supposed to be neighboring chords in this total order. So if we have two neighboring chords and this one is bigger than this one, and they don't intersect, then it's the same thing as we can exchange the order. Then it's this chord bigger than this one is the same as this one bigger than this one. So you cannot really even draw this, because we don't draw. The only way to draw the order on the chords is by intersection. So
number the chords.
Yeah. Well, yeah, you can draw it, but I mean, it's not n, it's I minus 1 is the same thing. So we have 4 parts. I mean, it's not very good because, no, it's okay, thank you. So this is the same as I minus 1. So this is the first move that would be invisible without the labels. And then the second move is a cyclic shift of all the heights. So what does it mean, a cyclic shift? So you see, if you have a diagram of this kind, and we have some chords here and there and all that, and one of the chords is on top of all of them. So let's say we have one chord that crosses over all of them. Well, we can just pull it and take it back. So the highest chord becomes the lowest chord, and everything else shifts 1 up. So this is the second move, which is probably not very interesting on the picture. And then there are 3 moves that look very much like the Rademeister moves. So the first Rademeister move is C1 is this one, plus or minus whatever. This is the same as nothing, interestingly. And it really is the first, I mean, if you draw it, it gets realized as something like this. And in order to untwist this thing, you untwist it twice. So it's like the double first Rademeister move. The second Rademeister move is, well, it's also something predictable. Plus and minus, it's the same thing as nothing. And then again, if you draw plus and minus here, well, something like this, and something like this, which is basically the inverse twist. You untwist it by the second Rademeister move twice also. And then there is the move C4. There is no move C3. There is a move C4. And this 1, 2, and 4, they refer to the number of chords that participate in the move. And the move C4 is a bit of a pain. So we have 4. Well, it's supposed to be. I mean, all the non-triviality of the knot theory lives in the third Rademeister move. So how does it work? It has 4 chords plus here. I have minus here and minus plus. So this is minus and this is plus. And this is the same thing as,
I'm lost.
well, everybody's lost. You're supposed to be lost. That's how it works. And minus here. Minus goes on top here. And plus goes here. So what does it mean? I mean, you can't really understand it in one instant. You need 2 instances for that. So this is a diagram that corresponds to this one. I mean, this is the realization of this move on the left. So what happens here is that we have a really interesting kind of tangling here. So if you kind of, well, I think it's a bit, yeah, something like this. So if you try to untwist it, what you really get is a symmetric picture. So with one clasp in the middle and the other one going around. And then you can do a symmetric thing, and then it becomes this diagram. So it is completely non-trivial. I mean, Pollock is clever. So once you realize that these moves hold, it really is quite non-trivial to show that they are sufficient to generate the 3 Rademeister moves. But it can be done. How do you do that? Well, the tool is the braid closure. You represent nodes by braids. Then there are some equivalences which are completely algebraic, and you fiddle with them, several pages of difficult pictures, and you are done. So this is a totally non-trivial fact. We struggled with it for quite a lot. I have to say that there are simpler moves. There are other moves that that are also valid, that involve 3 chords, and they're kind of slightly less intimidating than C4, but they're not sufficient. They do not seem to be sufficient to generate everything. So this, in a way, is a minimal set of moves necessary to produce nodes. So if you start thinking about these diagrams, if you try to think how Vassiliev invariants work in terms of these diagrams, it really is not. I mean, these things are really well suited for studying the Vassiliev invariants. So the universal Vassiliev invariant that people know and like or dislike is the Kontsevich integral. And of course, the reason why the Kontsevich integral exists, I mean, the reasons behind that, is that it's the Feynman integral for some, which you define in the Chern-Simons theory for the Wilson loop, which is some kind of a funny observable there that you construct out of a knot. It really is quite non-trivial. But what this Feynman integral produces is an algebra of Feynman graphs, and this algebra of Feynman graphs can be seen quite easily in terms of these diagrams. So the combinatorial meaning of the Kontsevich integral is completely unclear. Nobody knows what it means. I mean, unless, of course, you accept a Greenfield associator as a basic combinatorial object. Now, in other situations, like group theory, there is something similar to the Kontsevich integral, but much simpler. So basically, you take a combinatorial object and you send it to a formal sum object X, a formal sum of sub-objects of X. And for instance, if X is a word in a free group, and you can send a word in a free group into the set of into the sum of subwords in the free group, then you get something like a Kontsevich integral for the free group. And it's more or less something like this works here. So you take a diagram, and you send it to the sum of all the sub-diagrams. And of course, here we have some Rademeister moves. Here you have some, on this side you have some linearized Rademeister moves. So the problem of Vassiliev invariants becomes understand the set of sub-diagrams modulo the linearized Rademeister moves. It's not a simple problem, but it's not simple to solve, but it's very simple to understand. This is just very simple combinatorics involved. Again, simple to define. But this will be another story, I hope to. I hope to be able to give you an update someday.
Quick question? Well, thank you very much.